Hi everyone, I will discuss about the question number 8. I will read the question. The system consists of 1200 meter of 5 centimeter cast iron pipe, two 45 degree and 490 degree flanged long radius elbows, a fully open flanged globe valve and a sharp exit into a reservoir. If the elevation at point 1 is 400 meter, what gauge pressure is required at point 1 to deliver 0.005 meter cube per second of water at 20 degrees Celsius into the reservoir. So, this is our system. Elevation 500 meter. So, as given in the question here you can see there are two 45 degree flanged long radius elbows. Those are here, one is at 45 degree, one is at here, and for 90 degree long radius flanged. Those are 90 degree, 90 degree, then 90 degree and 90 degree. So, we have to calculate the gauge pressure at the point 1. So, for water at 20 degrees Celsius, we can take the density of water as at 20 degrees Celsius. At 20 degrees Celsius, density of water, we can take it as 998 kilogram per meter cube, and also the viscosity equal to 0.001 kilogram per meter second. And for the cast iron, we can take the roughness factor as epsilon equal to 0.26 millimeter. So that epsilon by d, the roughness ratio, which will be 0.0052, where d is in the question it is given d like diameter equal to 5 centimeter equal to, which is equal to 5 into 10 raised to minus 2 meter, okay, and L equal to 1200 meter. So, if we know the flow rate, we can calculate the velocity, and also from that we can calculate the Reynolds number. So, V velocity equal to flow rate divided by area. In the question, flow rate is given which is equal to 0.005 divided by area equal to pi by 4 d square into 0.05. So, velocity will be equal to 2.55 meter per second, and from that we can calculate the Reynolds number. Reynolds number equal to dV rho by mu. So, it will be equal to 0.05 into 2.55 into density 998 divided by 0.001, which is equal to, and from the Moody's chart we can get the friction factor. So, that you have to calculate, and you will get and there are minor losses and which can be listed as for 45 degree long radius elbow, 45 degree minor losses. For 45 degree elbow, K equal to 0.2. Similarly, for 90 degree, K equal to 0.3. And for open flanged globe wall, 8.5. Similarly, for submerged exit, K equal to 1. And also for the entrance, sharp entrance, K equal to 0.5. And if you are writing the energy equation between the point 1 and the 2, which is the reservoir surface, we can write the relation as since we are considering 2 as the reservoir, the gauge pressure will be 0. So, here we can neglect this, and also velocity is equal to 0. And these are the head loss due to friction, and this term is due to some bends, elbows and all. So, this term we can replace it as V square by 2G into FL by D plus sigma K. So, P1 by rho G plus V1 square by 2G plus Z1 equal to 0 plus Z2 plus V1 square by 2G this term is due to friction. Due to minor losses. So, from this we have to calculate the gauge pressure at point 1, that is P1. This one we have to calculate. For that P1 by rho G equal to Z2 minus Z1 plus V1 square by 2G FL by K plus sigma K minus 1. So, when we are substituting all the values, we will get 500 minus 400 plus velocity we got it as 2.55, 2 into 9.81 into, and from the Moody's chart we have calculated the friction factor, which is equal to 0.0 315 into length equal to 1200 divided by, sorry, this is D, diameter equal to 0.05 plus, and we are taking all the summation of this loss coefficients. Those are here we have two 45 degree, 490 degree and one open flanged globe wall, and also one submerged exit, and also we have one entrance, sharp entrance. So, we are taking all the summation which is equal to for the sharp entrance 0.5 plus for the 45 degree we are taking 2 into 0.2 and for 490 degree 0.3 plus this is for the exit, this is this is for the open flanged globe wall and this is for the submerged exit. After doing the calculation you will get 353 meter, and from that we have to calculate P1. So, P1 equal to 353 into rho g, which is equal to 353 into 9.81 into 998, which is equal to 3.46 megapascal. Coming to question number 9, I will read out the question. The pressure drop through a particle bed can be used to determine the external surface area and the average particle size. Data for a bed of crushed or particles shows delta P by L equal to 84 pound per inch square per feet. For airflow at superficial velocities 0.015 feet per second, the measured void fraction is 0.47 and the estimated sphericity is 0.7. Calculate the average particle size and the surface area per unit mass if the solid has a density of 4.1 gram per centimeter cube. How sensitive is the answer to an error of 0.01 in sigma? So, here what we have to mainly we have to calculate the size of the particle and then surface area of the particle, and also how sensitive it is if the error is 0.01 in sigma. So, first thing what we have to do is we know Cosny-Kármán equation. So, I will write that equation. Which is applicable for Reynolds number equal to, I will write the Cosny-Kármán equation where Reynolds number less than 1. So, delta P by L equal to 150 mu V into 1 minus epsilon the whole square divided by 5 dP the whole square epsilon cube, where mu is the viscosity, V is the superficial velocity and epsilon is the porosity of the bed, phi is the sphericity, dP is the diameter of the pellets, and delta P is the pressure drop, L is the length of the tube. So, here we have to substitute all the values. If I am taking phi dP the whole square in the left hand side, we can rewrite this above expression as mu V into 1 minus epsilon the whole square divided by epsilon cube into delta P by L. So, 150 into mu of air is equal to 1.81 into 10 raised to minus 5 kilogram per meter second. So, if I am writing in SI units 1.81 into 10 raised to minus 5, and velocity is given in the question, which is equal to in the question it is given in FPS unit, we have to convert it to SI units. So, in velocity will be equal to 4.572 into 10 raised to minus 3 into epsilon equal to 0.47. So, 1 minus 0.47 the whole square divided by 0.47 the whole cube into delta P by L, which is equal to 84. So, finally you will get so after doing the calculation you will get 1.89 no 84 is in, sorry, 84 is in FPS unit. So, here we are taking SI unit. So, I have to write in SI unit delta P by L is 1900,130.709. So, after doing the calculation you will get this as 1.89 into 10 raised to minus 10. So, from this we have to calculate dP, which is size of the particle. So, in the question sphericity is given as 0.7 and we also got the value of 5 dP the whole square, which is equal to 1.89 into 10 raised to minus 10. So, after substituting the sphericity we should we will get the size of the particle. So, 5 dP will be equal to first you can take root of this, and after substituting the sphericity you will get dP equal to 5.99 micrometer. So, this is first part of the question, and initially we have assumed that Reynolds number is less than 1. So, we have to check whether we are getting Reynolds number which is less than 1. So, for that we are just substituting all the values. So, after substituting all the values, you will mean if I am writing in FPS system 1, or you can write it in SI unit, whatever it is you will get the same. In question it is given both in SI unit and FPS unit, so we can use whatever you want. So, after substituting all these you will get Reynolds number equal to 1.8 into 10 raised to minus 3, which is less than 1. So, we can use the above equation which we have used initially. So, our assumption is correct. So, that we can say that the size of the particle which we got is correct. And the next thing is we have to calculate the surface area of the particle. For that we have the relation sphericity equal to 6 Vp divided by, from this we will get we have to calculate surface area of the particle. So, we have to calculate the surface area of the particle. So, we can write the this expression as Sp by Vp equal to 6 divided by 5s into dP, which is equal to 6 divided by 0.7 into 5.99 into 10 raised to minus 6. In the question the density of the particle is given as 4.1 gram per centimeter cube. So, here you will get the value as 1.43 into 10 raised to 6 meter square per meter cube. So, after substituting the volume you will get Sp equal to 1.43 into 10 raised to 6 into 10 raised to minus 6 into 4.1 gram per centimeter cube. So, which is equal to 5.9 meter square per gram. So, the surface area of the particle is 5.9 meter square per gram. And the other part is that if we are taking an error of 0.01 in sigma, how sensitive it is, that we have to find out. So, in the question initially it is given that sigma equal to 0.47. So, if we are taking an error of 0.01, the sigma will be 0.07. 0.46. If sigma equal to 0.046, what is the like how sensitive it is, that we have to calculate. For that we have the relation from the Korsney-Karman equation, that dp square equal to 1 minus sigma the whole square divided by sigma cube. So, dp2 divided by dp1 the whole square equal to 1 minus sigma 2 divided by 1 minus sigma 1 the whole square into sigma 1 divided by sigma 2 the whole cube. So, which is equal to 1 minus, initially it was sigma 1 equal to 0.47, sigma 2 equal to 0.46, 0.46 divided by 1 minus 0.47 the whole square into 0.47 divided by 0.46 the whole cube, and you will get it is equal to 1.086. So, dp by this is so we have to take the square root of this, dp2 by dp1 equal to 1.042 implies that dp2 equal to 1.046 of dp1, which implies that there is 5% increment in the size, or we can say error is 5%. I mean error is about 5% for an error of 0.01 in sigma value. This is the final answer. Thank you.